Hi, welcome to my channel, Jabertime. This is my fourth video today, and it's all about rational functions. This example is a focus on a hole on the graph, which is sometimes called removable discontinuity. You could see the graph. It's right there. And we have rational functions, as you could see, simplified, factored with colors. We're going to go over the whole thing in detail and show where's the hole and why it's right there. So let's get started. Graph the rational function f of x equals x plus 2 divided by x to the second minus x minus 6. Seeing it in factored form, the top part is x plus 2, of course. Now when you factor the bottom side, you get x plus 2 times x minus 3. Let's double check. Positive 2 times negative 3 is negative 6. Multiplying in, I get 2x. Multiplying out, I get negative 3x. Combining the 2x with the minus 3x, I get minus x. And of course, x times x is second. But what's interesting right here, if you notice, the denominator is telling me that I cannot have 3 because I can't divide by 0. Having x equals 3 will cause the denominator to be 0, and we're not allowed to divide by 0, or it's undefined, in other words. Same thing right here. We cannot plug in negative 2. But if I plug in negative 2, it's not the same behavior as plugging in 3. Plugging negative 2 will end up with 0 over 0. And if I simplify between x plus 2 and x plus 2 and cancel them, I get another fraction or rational function that's different. It's going to be 1 over x minus 3. But the only condition that I could do that is if x is not equal to negative 2. Because if x equals negative 2, as I mentioned, this will be 0, and this will be 0. 0 over 0 is undefined. So, excluding this value, I end up with this fraction. As you can see, I could keep talking, but let's summarize the ideas in writing. Under the topic horizontal and vertical asymptotes, we have cases for horizontal asymptotes in rational functions. There are usually 3 cases. This is one of them. If the degree of the numerator on top is less than the degree of the denominator at the bottom side, then we have a horizontal asymptote at the x-axis, which is y equal 0. If you need to see the other cases, I do have other videos, and I will link them down below and at the end of the video. Vertical asymptote comes from the factor that is not going to cancel. The horizontal asymptote, as you can see, the degree is less than. The degree on top is 1. The degree at the bottom is 2. So it does go with this comment. And that's why we have a horizontal asymptote at y equal 0, right there. Think about the vertical asymptote. I just mentioned that, so let's say it again. We look at the green part right there, and what makes it 0 is x equals 3. So here we do have a vertical asymptote, and the horizontal asymptote comes from having the degree down is higher than the degree on top, so the fraction is going to get smaller and smaller towards the value 0, which is approaching the x-axis as a horizontal asymptote. Of course, this also has another topic which is coming in the coming slides. So this is what we have. In case you simplify this, you have to mention that x cannot equal to negative 2. A hole in the graph. A hole is a point on the graph where the value of the function is not defined. And if the numerator and the denominator of a rational function have a common factor, this factor x plus 2 is in common between the numerator and the denominator. They will cancel when simplifying, of course. We'll cancel them, but we have to keep that in mind. The cancelled factor, so the whole focus is on x plus 2 now, creates a hole in the graph. This is the factor. So what makes this factor 0 is actually x equals -2, which means we have a hole at x equals -2. So we talked about the horizontal asymptote 0 because of the degrees. We talked about the vertical asymptote coming from x minus 3. And now we're talking about a hole in the graph coming from x plus 2 as a common factor. A hole in the graph, a vertical asymptote. Moving on. To graph the function with more details, we need the x-intercept and the y-intercept. For the x-intercept, usually what we do, we plug in y equals 0. Because when you cross the x-axis, y equals 0. But if you do it without thinking enough, it might pass by you and you'll end up with a mistake. Let me show you what do I mean. So y equals 0. Here's a fraction as it was given to me. But a fraction like this will equal 0 if the numerator equals 0, meaning x plus 2 equals 0. Then I would say, okay, so the x-intercept is x equals -2. But that's not true. That is not true. We talked about that. Let me show you what I mean. This is our function, which is written right there. If you factor it, we're not allowed to plug in 0. We focused here on the numerator. But x equals -2 will cause the denominator to be 0, which means I'm going to end up with 0 over 0. So that's not my x-intercept. It's not. It's actually what we talked about as a hole on the graph at x equals -2. Just be careful right here. We don't have an x-intercept. We have a hole at x equals -2. For the y-intercept, we just plug in x equals 0 and simplify this. 0 here plus 2, 0 square minus 0 minus 6. We'll end up with 2 over -6. Simplified to -1/3. And that is my y-intercept, just below the x-axis. Let's talk about the domain and range. Usually, most math books, they focus on the domain for rational functions, but I believe it's interesting to talk about the range also. So the domain is all real numbers except the values that will cause the denominator to be 0. At x equals 3 we can't, because that's going to be 0 here. That's a vertical asymptote. At x equals -2 we can't, because that's a common factor, which is a hole in the graph. So we do have a hole at x equals -2. We do have a vertical asymptote at x equals 3. These two values should be taken out of my domain. As a set notation or interval notation, we could rewrite it this way. From -infinity to -2, not including -2. Union from -2 to 3, not including -2, not including 3. Union from 3 to infinity. Same thing. Alright? Now the range. I mentioned that it's interesting. So let's talk about the range. You know that we have a hole at x equals -2. So if it's filled, it's going to have a value. But that value should be out of my range because I don't have an image there. The y values are not defined when x equals -2. So if x equals -2, we could play the trick here and use that in the simplified. Well, in this graph, it's a graph that I'm skipping -2. But if I connect it, I'm going to plug in -2. So 1 over x minus 3 will be 1 over -2 minus 3, which is 1 over -5. Pulling the negative up front, that will be -1/5, which is 2 over 10, which is -0.2. So if I fill the point, it's going to be filled with that y value at x equals -2, which we agreed on that we have a hole in the graph. So the range will be, we talked about the horizontal asymptote as the x-axis. So y cannot equal to 0 because we have a horizontal asymptote because of the degrees. And it can't be an image when x equals -2 because that's a hole. But if you want to find it out, that's the value. So that should be also taken out because we don't have it. So the range is all real numbers except when you have a horizontal asymptote, and except the value when you have a hole in the graph. And the hole in the graph happens to be when x equals -2. As you could see, this is more interesting than the domain, but most books, they keep asking about the domain. They don't ask about the range, but the range is interesting. Let's move on to the graph. We're almost done. So for the x-intercept, we said we cannot plug in -2 because -2 will make a 0 over 0, and there's a hole on the graph at that x value. That's not going to be happening. If this is x plus 5, yeah, -2 will make it 0 over something, which is 0. But no, we don't have an x-intercept to cause y equals 0. Quickly, let's go over this. Horizontal asymptote at y equals 0 because the degree down is higher. So the value of the fraction will go down to 0. The vertical asymptote comes from this factor right there. A hole in the graph comes from the common factor right there. The y-intercept is when you plug in 0 for x. I get 2 over -6 simplifies to -1/3. The domain, all real numbers except what you cannot plug in, that causes the denominator to be 0. So you can't have a -2 and you can't have a 3. The range, I talked about it in detail, cannot be at the level of the horizontal asymptote at the x-axis, and it cannot be the output value when x equals -2 because that's a hole in the graph, and that y value is out of my range. Now let's graph it. We'll start with the horizontal asymptote, which is the x-axis right there. That's my x-axis. Then we'll go to the vertical asymptote at x equals 3 right there. Then we mark the hole in the graph when x equals -2 right there. Why I have it too close to the x-axis? Because you remember this value? That's like -0.2. If it's filled, that's the value of it. Which is good to know, because if you have no idea, you might go like a little bit down here. But that's not a very good graph. Of course, when you graph by hand, it's not going to be perfect, but to the best that we can. So we talked about the domain and range, but the graph is going to support that. So let's move on. We have an x-intercept none. We have a y-intercept at -1/3. So somewhere right here, that's y equals -1/3. So let's mark it right there. So I do have a graph that is gonna go close to this vertical asymptote, and it's going to get close to this horizontal asymptote, passing this point and skipping this point. Here we go. The other piece will be up here, and I think I'm done. This is my 4th video today about rational functions, and I think I covered kind of all aspects of rational functions to the best that I can. If there is more needed later on, I'll add more examples. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.